To finish up this discussion on enthalpy, let's look at what's known as a state function. A state function is a function where the path is not relevant to the outcome. If you look at the, say, potential energy moving from the base of Kilimanjaro here to the surface or to the top of Kilimanjaro, the summit, it doesn't matter how you get to the summit. The potential energy that you have when you get to the summit is the same. However, if you're looking at distance, which is not a state function, then the path that's taken is very important. Enthalpy is a state function. That is to say, it doesn't matter what path you take to get where you're going. The change in enthalpy will be the same regardless of the path that's taken. Enthalpy is the sum of the internal energy of a system plus the pressure volume state of that system. So the enthalpy of any particular situation or system, remember system is a part of the universe that you separate out and decide to look at. In chemistry, it's usually a chemical reaction or a chemical situation. It's the internal energy that situation has plus the pressure volume state, and that pressure volume state basically represents the work that the system does. So the change in enthalpy is equal to the change in internal energy plus the pressure times the change in volume, assuming a constant pressure. And that change in volume against constant pressure is the same as the work done by the system. And so that's why it has a negative W sign. But also remember that the change in enthalpy from its previous slides that we looked at is equal to the heat of reaction plus the work done on the system. So that means that the change in enthalpy will be equal to the heat of reaction plus the work minus the work. So the change in enthalpy is equal to the heat of reaction, which is equal to the heat of the products of the reaction. And this is an important relationship to remember. So if we look at the enthalpy of any particular system, let's take, for example, the formation of water from hydrogen and oxygen. If you take gaseous hydrogen and add water to it and form liquid water, the change in enthalpy of that reaction is negative 286 kilojoules, which means if that reaction occurs, then 286 kilojoules of energy are produced as one of the products of the reaction. If you do the same reaction, and the only difference is that you form gaseous water instead of liquid water, it changes the enthalpy from 286 to 242 kilojoules. Now, in some respects, this makes sense because you expend some of the energy converting liquid water into gaseous water. Remember that the negative change in enthalpy sign means that the heat is a product of the reaction, and it's an exothermic reaction, and a positive change in enthalpy means you have an endothermic reaction where heat is a reactant. Now, one concept that you need to understand as we move into this discussion is the idea of a steady state, or standard state, excuse me. You might remember back in basic science and maybe in physics if you were in there, the concept of standard temperature and pressure. This was a concept used in the gas laws, and it was a means of identifying a set of conditions in which 1 mole of any particular gas would occupy a standard volume of 22.4 liters in these standard conditions. So A standard set state is any common set of accepted conditions that can be used as a reference point. So in the area of enthalpy, there's something known as the standard enthalpy of combustion. And what that standard enthalpy of combustion is the heat that is either produced or absorbed when 1 mole of a substance is completely combusted with oxygen. Now, generally, when we talk about combustion, we're talking about heat that's produced. But the idea here is that you're using 1 mole of a substance. And so, for example, if you combust 1 mole of alcohol, ethyl alcohol, the standard enthalpy of that combustion is minus 1,366.8 kilojoules for that 1 mole. Another standard is called the standard enthalpy of formation. The standard enthalpy of formation, which is abbreviated DH sub F 0, 0 meaning standard, is the change that occurs when 1 mole of a substance, a pure substance, is formed from its elements. And so, for example, if you look at the formation of water like we did previously from its elements, the standard enthalpy of formation would be how much heat is either produced or used to produce 1 mole of water from hydrogen and oxygen. Now, this diagram is a diagram to illustrate Hess's law. And Hess's law is how we go from the elements, carbon plus oxygen, and end up with carbon dioxide. Now, one way to find that is to actually go through 2 steps, carbon plus oxygen to form carbon monoxide, and then carbon monoxide plus another oxygen to form carbon dioxide. And you can add the heat of formation from here to here to the heat of formation from here to here, and the total will equal the heat of formation from the top to the bottom. And that's what Hess's law says, that if you write a process in a stepwise manner, then the heat of formation is equal to the sum of the heats of formation of the various reactants. And so you can take the heats of formation of the products, subtract the heats of formation of the reactants, and that will give you the enthalpy for that reaction. Remember that the heat of formation is per mole, so if the equation has 2 moles, you multiply by 2. If it's a half, you multiply by half. You also have to remember that if you reverse the direction of a reaction, then the H, heat of formation, is the same, but the sign changes from negative to positive or from positive to negative. So let's look at a couple problems on how Hess's law would be used. And here's the first problem. And I'm going to write this down because it doesn't write that well on when you type it. So we want to see what the enthalpy is for this reaction. N2 plus 2O2 reacts to form 2NO2. Now we know, first of all, we have this, which says that, so that's what we want to end up with. This right here is what we want to end up with. First of all, we know that N2 plus O2 goes to form 2NO, and that has a DH of plus 180.5 kilojoules. And we also know that NO plus 1/2 O2 goes to form NO2. Now, up here we want 2 NO2. We only have 1 NO2 here, so let's multiply this bottom one by 2. I need to write in that DH there is minus 57 57.06. So if we multiply this by, if we do this and add these two together, if we end up with N2 plus 2 times NO plus 2 times this is 1, and then one more is 2O2, goes to form 2NO2 plus 2NO. Now the nice thing here is that cancels out with that, and you end up with this. And so all you have to do is multiply this 57.06 times 2, and then add these two together, and you have the answer. So DH is going to be, say, 114, so that's 66 there, and 0.12 from that is 38 kilojoules per mole. And so this is a pretty simple, straightforward one. Now this next one is actually pretty difficult, and I'll just tell you that the answer to this is also on page 267 and 268 of your book if you have trouble following what I'm telling you. But what you want to end up with is CLF plus F2 is equal or to form CLF3. Okay, that's what you want to end up with. Now, if you look at these three equations here, you want to end up with CLF in the reactants. Well, you have that in this middle equation here, but you have to multiply it by a half. So let's do that. We'll multiply CLF plus 1/2 O2 to form 1/2 Cl2O plus 1/2 of that, and use a half of that number. So that's going to be CLF plus 1/2 O2 goes to form 1/2 Cl2O plus 1/2 OF2. And if we take half of this, we get DH is equal to 102.8 kilojoules. Okay, so that gives us this on this side. The other thing we want on that side is F. And let's see if we can find that. Here, this top one has F in the products. You end up with this, so you get it from this. So but you only want one of those, so let's take half of this one too, okay? So that's going to be F2 plus 1/2 O2 goes to form OF2. And it's another half, so that's going to be the DH here is going to be 1/2 of this number, which is 24.7 minus 24.7 kilojoules. Now the third thing we want is this guy. We actually need this on the product side, okay? So we're going to reverse this one, okay? So when you reverse it, you just change the sign. So that's going to be Cl2O plus 3/2 OF2 goes to form CLF3 plus O2, and DH here is now going to be, instead of a positive, it's going to be a negative 266.7. Now let's see what happens when we add all this crap up, okay? If we add all these up, we end up with CLF, which we want, plus F2 we want, plus Cl2O, plus O2, plus 3/2 OF2. So that's all of these things on this side. And we go on the other side, and we have one half Cl2O plus 1/2, or excuse me, 3/2 OF2 plus ClF3 plus O2, okay? Now, the one problem here is we've got a half here. Did I do that right? Yep, I think I did. Okay, so we're sitting here with a half here. Now, the good news is with this, we get rid of this, and that cancels that guy out. We get rid of this, and that cancels this guy out. And what we're ending up with is ClF plus F2 plus Cl2O goes to form 1/2 Cl2O plus ClF3. And is there some way that I can get rid of this guy right here? Did I make a mistake? I don't think I did. But as I said, the answer is on page 267 and 268. If you look at the answer on page 268, for equation number 4 that they say in the answer book, when they reverse, they change the Cl2O to 1/2 Cl2O, and I do not see how they do that. Because it does not seem to me they 1/2 all of it. In other words, when they copy this one down, they reverse it, they make this a half, and I'm not seeing how they pull that off. But you see the idea here, and I wouldn't give you one this hard on a quiz or a test, but you see the idea here is to manipulate these in such a way as to end up with what you want to end up with. And right now this is ClF plus F2, and I have left a half Cl2O to get ClF3, and I'm not sure what happened with these various equations when I look at the answers that it'll get that. So I'll stop at this point, and if I figure out what I did wrong, we'll talk about it in class.